Okay, so I'd like to do what I think is the most substantial problem that I've done so far, all right? And I think it's a really, really nice one. It's one that you'll get to do again in graduate school if you do it. I mean, I remember doing this first is in graduate school. Usually, you just get the results, right, as an undergraduate. But in graduate school, you get to do this all by yourself. And I mean, it's a really fun problem. I'm not sure how many problems there are that actually get a nice solution like this, but it's one of the few that does. So what we're going to do is we're going to look at this charged particle in close to this conducting sphere. We've got a conducting sphere that's grounded, right? And this charged particle is going to induce a charge on this, and actually that charge is going to bring, going to attract this particle here. We're not going to worry about the attraction. The attraction, I've given you a homework problem on that. All I want to look at right now is what happens with the charge distribution here. So this is a supplement to what we do in class. In class we do the parallel plate capacitor. That's something we can do in a reasonably short amount of time, and in 15 to 20 minutes, and still have time for discussion and things like that. This problem, however, is a little more complicated. It requires a lot of different little parts to it. And, I think I'd really, really like to go through and make sure that you've seen all of that, at least at one point in your life. And, obviously, this is something that you're going to get to do over and over and over again. Well, a lot of the things I'm doing here are things you're going to do over and over again in simpler settings. You've seen it in a simpler case before. Let's see what happens in a more complicated case where you've got all sorts of variables running around. All right. Okay, so let's just rewrite what I just said. Right. So I said that we had a grounded conducting sphere. Okay, that's our favorite, a grounded conducting sphere. I'm actually agnostic about what's going on the inside. It doesn't really matter. Is it a spherical shell? Is it a solid sphere of copper? Or actually it should be a perfect conductor, so it should have, it should be a better conductor than anything real. But in any event, is it just a big ball of some perfect metal? Hey, it doesn't matter for what we're going to do today, right? So we have some sort of radius to this sphere. It's going to be r. We always need some sort of radius r. And then we have some sort of charged bead, right? I like to use charged beads because that sounds more like we've got a really small charged object than we have some point particle that isn't really real. Okay, and we've charged that bead up to Q before we brought it over near the sphere. And we've brought it a distance d to the sphere. Now, what does a distance from an object mean? It means how far you are to the sphere. Okay. It means, the closest distance from here to here, the closest distance between the object and the point, or the closest points on two objects, the distance between the closest two objects of two objects. So that's more or less what that distance is. So the distance d is here, the distance r is here. So from the center of the sphere to the charged bead is r plus d. That's something we're going to have to use. The concept here. So we're going to have to use Gauss's law later. There are lots of little parts to this problem, but the big concept is, of course, the method of images. All right. So the method of images says that we take the case where v of r is equal to 0. So everywhere around here, it's identically 0, no potential. Let's change the potential to phi, just because I know what's coming up and what I've written down in the later part of the lecture. I guess this isn't a lecture. Maybe it's a lecture. I don't know. Okay. So we've got phi of r here equal to 0, and because of that, we can find on the inside a charge, an imaginary charge that will give us the same result as if we knew exactly what the charge distribution was here in the first place. Okay. And if we know what the result of that charge distribution is, we can use Gauss's law to go ahead and find the charge distribution itself, right? So, you know, all that stuff from the previous semesters or the previous 2 units, this problem uses a bunch of the stuff from the previous 2 units, okay? So, you know, these things build up, try to keep up. If there's a problem with something you don't remember, go back and read about it, right? That's why you have a book. I mean, I think both of you who are likely to watch this are pretty good about it, but I've had semesters where it's been obvious that some of the students don't like that idea. Now, this is going to be a very important problem to actually be clear about where everything is. It's going to be really, really important for us. So we're going to need to place the sphere at the origin. Okay, and we're going to want to, so if we do our drawing up here, right, so we have our sphere over here at the origin. So I guess I should have said I placed the center of the sphere at the origin. So we place that at the origin. And then we want to put this this charged particle somewhere, this charged bead. We'll put it right up here on the z-axis. Okay, and we're going to do a lot of work with vectors in this thing, so we better be pretty clear about our vectors here. So our vectors are for the bead, x1 is equal to, we said, d plus r. D is from here to here, r is from here to here. Radius, distance, r plus d in the z-hat direction. Then we have, on top of the bead, we have the sphere. Okay. And the sphere, every point on the sphere is going to be radial from the center, right? So each point on the sphere is x hat plus y hat plus z hat, but we have a condition, right? And the condition is it's at the edge of the sphere. And you know, to be at the edge of the sphere, that means the sum of the x, the y, and the z positions is equal to the square of the sum of the squares of the x and y and z positions, coordinates, excuse me, is equal to the square of the radius of the sphere. Okay, and this is going to show up later on in the analysis. So, you know, a lot of times when I've done this, this hasn't really shown up in the analysis. This does happen in this case. So everything's important in this case. And this isn't even the hardest problem you can do like this. All right, so this B-type problem, this B-type problem rubric that I'm using, that is intended to make sure that you're used to using these, because as we get farther along in the course, this is going to get more and more important. Okay, so please write these things down. With these type C and B problems, come to me and let's talk about those vectors if you don't know how to write them a day or two before, or 3 or 4 or 5, or however long before you can get. Before everything's due. I mean, you should probably try to set up all of those problems the day that you get the problem set. All right, just try to set them up. See what you can do. Because if you don't know the geometry, you can't do anything. I think I read that to you in class. That one quote from the inventor. Everything I do is geometry. Or I guess he was an engineer, but still. Everything I do is geometry. I just have to put this here and that here and that's here. And it's true. Everything you do for a long time is going to be geometry. There are a few places where there's not so much geometry. There's a lot of geometry in physics, and there's even more in engineering. Okay. All right. So my strategy. Okay. Well, I'm going to use the method of images, so I'm going to have to place a general image charge. So, I'm just going to put an image charge somewhere inside of this sphere, right? So it has to be, the image charge has to be somewhere inside of this sphere, right? That's what we said before, is that the image charge has to be, the image charge can't be anywhere in the real space. It has to be somewhere beyond the border of our conducting material, right? It has to be somewhere inside the conducting material if we say the outside is where our real charges are. So it has to be somewhere in here. We're going to use symmetry conditions to figure out that it has to be along the z-axis, but we'll do that in just a second. So in this case, I'm going to do the entire strategy on this one page. Okay, and the reason is because we've got two big steps to do this. First is finding the image charges, and second will be to find the charge distribution using Gauss's law. All right. So first we place that general image charge in there, and then two, we start finding potentials. So we need the potential at this place to be 0. Obviously it can't be 0 from just one charge as long as Q is greater than 0. So we need another charge in here. So we're going to find, from using the sort of general image charge things, the position, which is a variable, and which is an unknown thing, and the charge, which is an unknown thing. We'll just give them some labels, and we'll figure out what they are in terms of these real quantities. All right, and we'll do that by writing the potential, and we write the potentials from both charges. Okay, and then we got to sum them. We've got to superimpose them. Let's not make that a secondary a second task. It's still part of the same task, really. Then we're going to have, we've got these two unknowns, like I said, the charge and the position. We're going to have to find two equations somehow, using the potential so that we can use this condition. Okay, so we're going to just have to choose 2 points on the sphere, and so we'll talk about how and why we choose those 2 points. But we need 2 points on the sphere to create 2 equations, so we can get 2 unknowns. So then we'll construct those equations. All right. So everything's simple so far. I'm pretty sure that you're keeping up right now, right? And then what we're going to do is we're going to take some time to simplify things. That's going to be very important because we're going to have denominators and numerators and stuff like that. And we'll just simplify the equations so that we can manipulate them pretty well, and then we'll solve them. We'll find Q prime and x2 prime. It's really x2. We don't need the prime, but hey, let's keep them all together. So that's task 1. Task 2 is going to be to use these to find the charge distribution on the sphere. Okay, so to do that, we'll first find the fields using Coulomb's law. So we don't need to do anything fancy. We don't need to take the gradient of the potential, even though we've got the potential over here, right? We don't need to take the gradient of the potential because we already know what's going to happen. Thanks to finding an image charge in here, we don't have to worry about We don't have to worry about charge distributions. We don't have to worry about anything else. The field is just going to come from these 2 point charges, and we've been doing that since day one. So we are good with finding fields with Coulomb's law. So let's just do it, okay? And after that, we'll transform to spherical coordinates. And now, the reason why we're going to do that is because, well, it's because, you know, our final answer should not really have any dependence due to symmetries. Should have no dependence on anything except this theta angle, right? This polar angle is the only angle that really means anything. The azimuthal angle, useless. The radius, constant, right? The azimuthal angle, again, symmetry says it shouldn't make a difference. So if we go to spherical coordinates, then we've got two variables that don't mean anything, and one that does. So we'll be left with an answer in one variable instead of 3. Now, that'll be great. And I know you'll love having more. I know you love more variables, right? I know you love doing complicated, extremely, amazingly complicated things, just so that you can confuse me. But really, we want to make sure that everything's simple. So after we do the transformation, things will be messy, so we'll need to simplify some stuff. And after we do that, I'll superimpose. Superimpose. So after we superimpose those solutions, everything's going to be cool again, right? We'll be happy again. And at that point, we're ready to use Gauss's law. And using Gauss's law, we will, once we get Gauss's law going, then we'll be able to do whatever it is we need to do. Well, actually, Gauss's law will find sigma, right? Gauss's law finds sigma, which is what I should have written up here. Sorry, I forgot to write that up there. But already this video is about 7 minutes longer than the first one that I did, even though I only made one small error in something I said there, and I decided that I had to redo it. It's a big enough error that I didn't want you ever hearing it. But it wasn't really meaningful in the context of the problem. So I will be back in just a second, and we'll start going down this strategy and do all of the vector calculus that you ever wanted to do. Is there any calculus in here? Yeah, there's a little bit of calculus. You'll love it. Okay, I'll talk to you later.